This video is about static equilibrium. After working through this assignment, you should be able to use a diagram to indicate the forces, lever arms, and torques exerted on an object, and perform calculations relating the forces and torques on an extended object in static equilibrium. To get the most out of this video, you should have a solid understanding of drawing a free body diagram when forces are exerted on an extended object, calculating torque by the lever arm times the perpendicular component of the force, or the perpendicular component of the lever arm times the force, and Newton's second law, both for translation and rotation. You already know that if you apply a net force to an object, that object will accelerate, and if you apply a net torque to an object, that object will rotate with an angular acceleration. But if you oppose that force with an equal and opposite force, the object won't accelerate, and if that object was initially at rest, it'll remain at rest in static equilibrium. If you apply equal and opposite forces to the object as well as equal and opposite torques, then with a zero net force and a zero net torque, the object will have neither a linear nor angular acceleration. If that object was initially at rest, it will not move or rotate. These are the conditions for static equilibrium. When an object is in static equilibrium, it doesn't move and it doesn't rotate. Here, a beam rests on a pivot, with unequal weights resting on either end. For this system to remain at rest like this, the forces and torques acting on the beam must balance. Mass 1 exerts a downward contact force on the beam equal to its weight, as does mass 2. The force of gravity on the beam is also downward and acts at the beam's center of mass. The pivot provides an upward normal force on the beam. You don't know the magnitude of this force, or where it's exerted on the beam. These are things you can determine using the conditions for static equilibrium. This gives a free body diagram that you can use to relate the forces and torques acting on the beam. Since the beam is in static equilibrium, the net force must be zero. The vector sum of the forces acting on the beam is the normal force minus the weight of mass 1 minus the weight of mass 2 minus the weight of the beam, and this equals 0. Add the negative terms to the other side to solve for the normal force and factor out the g. Given the three masses, which add to 6 kilograms, you can find the normal force of 59 newtons. But where do you need to place the pivot so that the beam is in static equilibrium? You can use torques to determine this. First, decide where to put the origin. This is the reference point you'll use to measure all the torques acting on the beam. Put this point at the left end of the beam, where mass 1 exerts a downward force. You can put this point anywhere you'd like, and as long as you're consistent in your torque measurements, you'll always arrive at the same result. The pivot is a distance r sub n away from this point, and this is what you want to find. Mass 2 is a distance r2 away from the origin, and the force of gravity on the beam, m3g, acts at a distance r3 from the origin. These forces exert torques on the beam about this reference point, and all of those torques sum to 0 since the beam is in static equilibrium. Mass 2 exerts a clockwise torque about this point, as does the weight of the beam. The normal force exerts a counterclockwise torque to balance the other two torques and keep the beam in static equilibrium. Mass 1 exerts no torque on the beam since it's exerted at a distance of 0 meters from the origin, or the axis of rotation. The vector sum of these torques is minus r2 m2g, where r2 is the lever arm, or the distance from the origin to where the force is applied. This torque is negative because conventionally clockwise rotation is defined to be in the negative direction. Subtract r3 m3g because this torque is also in the clockwise direction. Then add r sub n times n because the torque from the normal force of the pivot is counterclockwise. This all equals 0 due to the beam being in static equilibrium. Add the negative terms to the other side to solve for the torque exerted by the normal force, and divide by the normal force to solve for the lever arm of the torque from the normal force. Given r2 and r3, you can find r sub n by substituting in the values you know. To keep the beam in static equilibrium, the pivot needs to be 0.58 meters from the origin. Now imagine that a ladder of length L rests against a smooth glass wall and makes a 55-degree angle with the floor. 2/3 of the way up the ladder is a person, and the ladder remains in static equilibrium. Draw a free body diagram of the forces acting on the ladder. The weight of the ladder, m sub lg, acts at the ladder's center of mass and points straight down. The force that the person exerts on the ladder, m sub pg, also acts straight down. To balance these downward forces, the floor exerts an upward normal force. The glass wall also exerts a normal force on the ladder, but call it F sub wall to distinguish it from the floor's normal force. Since the glass is smooth, it doesn't exert a frictional force on the ladder, but the floor does. To keep the ladder from slipping away from the wall, there's a static frictional force that keeps the ladder in static equilibrium. What's the magnitude of the torque that the ladder's weight exerts on the ladder, measured with respect to the origin at the base of the ladder?